It's very nice being here, such a diverse audience, very different from the typical classroom I'm in. Physics students, engineers, it's quite boring. I'm very excited being here. I would call myself a typical analog dinosaur. It's nothing to do with digital. But I think this is also what we're doing all the time in chip design for neuromorphic circuits, because this is what is really accelerating AI developments at the moment. We are creating neuromorphic chips trying to imitate what the brain does. But from a neuroscience perspective, I think we're very bad in what we are doing. Because if you compare, for example, a typical CMOS chip like here, on the right-hand side, we have top-down engineering, fixed connections, rigid material, everything written in stone. But on the other side, we have a biological system where everything is in a wet environment. Everything is just very fuzzy, random, talking to each other. And it's actually changing over time, all the time. It's growing, you're pruning things, etc. So there's a very big difference from our vision how computing works in software and hardware at the moment in silicon and what our brain really does. And I think if we want to accelerate the development of AI further, in particular for edge applications, we have to look more deeper into the materials and the concepts that we also find in our brain. And in particular, this permanent change of synaptic connections, so the growing of synaptic connections, also the cutting of synaptic connections, is something very, very important. And we call this effect in neurobiology structural plasticity. So if you're young, you have a couple of neurons, but practically they're not connected to each other. So this is the situation. If you're young, 1 month, there are a couple of neurons and synapses, and they are growing over time. And this process stops at the age of about 10, and then you start pruning the connections. You're taking them away. And this makes your network very efficient. You have to cut certain connections out. And this is a very important mechanism in biology in order to, let's say, learn effectively in a sparse neural network. You have to grow new connections, and you have to cut them out. And this has been shown in many different studies how it happens over the phase of your life. You're starting as a young person. There are basically almost no connection. They are growing until the age of about 10, and then you really start cutting the connections. So we are learning something by taking connections away. That's actually quite surprising, but that's how it works in our brain. And we ask ourselves, well, is there a possibility to do this with hardware? And to be honest, if you look in literature, there's almost nothing you can do in silicon-based hardware. You can over-engineer a circuit, make thousands and millions and billions of connections, then just leave them. You're not cutting them away. So it's very tough to emulate this structural plasticity with a hardware-based system. So, but we thought, okay, is there anything we can do just to mimic this very efficiently? And we found a process that you might be all familiar with somehow. It's called electropolymerization. You might know that from nylon fibers making or from cotton candy. You're applying heat or electric field, you're putting sugar in, you grow huge fibers. That's cotton candy. And we are doing, in principle, the same thing. We are using 2 electrodes just on the substrate, put a droplet of water and a grain of salt into that. And in the liquid, we have a polymer that can polymerize up and applying a certain amount of temperature or an electrical potential. And what happens now, if we put the monomer into the solution and we apply a potential, we start growing these kind of small connections here. And these are electrically conductive. But they're not only electrically conductive, they also have very specific synaptic properties because they always work in solution. They communicate with ions. That means they have short-term, long-term plasticity, but also other higher orders of structural plasticity. And this is something we have studied very much in detail. We have developed models how to grow these connections. It takes about 2 seconds to grow 1 connection. We can make this really at every spot on a chip. We can make these connections. And we have, let's say, checked all the timescales of synaptic plasticity, which are important to implement learning really efficiently in hardware. But the key of that is to make a big network, to do something meaningful, and really something meaningful that is for our life, for the society. So we thought, okay, how we can make something complex and also make an impact with that. And we went further, or this is just a toy example I would just briefly show, just to illustrate you the idea of structural plasticity. It's a complete oversimplification, but at least you can see what happens here over time. This is the idea of Pavlovian conditioning. So you have a trigger, which is basically food and the bell. And initially, there's a connection between the food and the salivation, so it's already there. And only if you ring the bell and provide the food at the same time, you're growing over here in the third picture a new connection. So that means you create a synapse which remains there. You can improve the strength of this connection, but you can also, let's say, fade it away over time. But we want to go one step further and make full networks out of that. And this is how it looks like in reality then. We are calling this a so-called reservoir. We have a couple of electrodes just on the chip, put a droplet of water, and grow these fibers. It takes 3 seconds. It's completely random. There's no engineering in that. It emerges. You can put it on your finger, like here on a substrate of gelatine, so it's actually biocompostable. And it can recognize your heartbeat. It can recognize your blood sugar values and everything like that. And this simple piece of polymer already has an intelligence because it has an intrinsic synaptic plasticity and nonlinear properties, which we are harvesting for this particular system here. And just to give you a few examples that we have shown in the last few years, this is a classification task of heartbeats. You really put this on your finger. You can recognize your heartbeat. And the most simple system, just randomly grown, gives you like 92% recognition accuracy of such a system. If we implement structural plasticity, meaning we are modifying the system a little, then we can go up to 99% just with the simple piece of polymer. That's all. Also for time series prediction, something very useful if you want to predict, for example, the temperature rise in the human body in order to predict whether there is a lethal infection going on. You can use this system also here. This is the graph at the bottom with an accuracy of about 97% for a typical time series prediction. But to show you the vision we are currently working on, so for those of you who are a bit, let's say, sensitive, you might look away because this is now the real application we are targeting for. We are putting our small plastic brain onto chips that you can put into your body. For example, for column surgery, if you have a leakage in the column itself. You can put this chip into your body, and it recognizes certain, let's say, features of an infection, like change of pH value, change of temperature, other kind of indicators, and you can predict at a very, very early stage whether there's a dangerous situation appearing. And this is our main vision, that we would like to utilize the structural plasticity and these very simple polymer fibers that you just grow randomly on a substrate as an ideal human-machine interface that you can put into your body. It actually disappears over the course of several weeks, and you just continue living. It's monitoring your condition very, very easily and efficiently. And this is already my last slide. I see I still have 4 minutes, so maybe I just do a very short pitch on that, what we're doing right now. Since the IPP, so the institute I'm working on, is quite famous for its track record on spin-off companies. I think in the last 20 years, we had 15 successful spin-off companies with an overall, let's say, revenue of, I think, 600 million at the moment. So we're very active in that, and that's also what we're trying to do at the moment with this particular technology. We are part of the Sprint initiative of the Bundesregierung, and we're trying to put this into practice, looking for application scenarios in the body where we can harvest this specific kind of AI, which is completely biodegradable, low power, and it's very easy to make. Thank you so much for your kind attention.